Record this. So starting with the first thing, what is enthalpy of formation delta HF? We did cover this in AS. The standard enthalpy change of formation. Was that any idea?
Yeah.
So
is it the change for formation? So it's the energy released / taken in when 1 mole of a substance is formed?
so it's the, I mean, not, it's energy that is released or absorbed. So it could be both. It could be positive or it could be negative, end or exo. And when what happens when 1 mole of a substance is formed, so when 1 mole of a substance is formed from its constituent elements and measured under standard conditions. So that's what, and the main thing is 1 mole of a substance getting formed from its constituent elements. So if you have NaCl solid, 1 mole getting formed from its elements, the elements are for NaCl, it's going to be NaN, it's going to be NaCl2. N is going to be solid and Cl2 is going to be a gas, and there's going to be half Cl2 because it always has to be 1 mole of a substance that's getting formed. So that's equivalent to delta HF of NaCl. What is the enthalpy of formation of ethanol? Do you know what the equation is? How would you write the equation?
No, I'm not sure.
What's the formula of ethanol?
C2H5OH.
So 1 mole of ethanol, C2H5OH, liquid, which is going to be formed from its elements. The elements are what? Carbon. And the other element is hydrogen, that's H2. And you've got oxygen, which is O2. And there's going to be 3H2, and there's going to be half O2 and 2 CO2s. In gas. Okay, so this enthalpy change would be enthalpy of formation of ethanol, C2H5OH. Tell me the enthalpy of formation of aluminium oxide. What's the equation?
Is it 2Al plus 3O?
Oh, we can balance it later. It's Al plus what?
Oxygen.
Which is O2. And together they're going to form Al2O3, right?
Yeah.
That's a solid. This one is a gas. This one is a solid, and there's going to be 2Al and 3/2O2, right? Okay, so that's the enthalpy of formation of Al2O3. Now, the next thing is, that's enthalpy of formation. Remember, different reactions can have different names to the enthalpy changes. Okay, same reaction. Can have different enthalpy change names. So for example, if you have C plus O2 and it's forming CO2, so you can call it enthalpy of formation of carbon dioxide, or you can also call it the enthalpy of combustion of carbon as well, right? So is this clear that I mean the reaction can have multiple? I mean its enthalpy change could be named differently, right? That's clear.
Yeah.
So the next thing is that when it comes to enthalpy change of formation, always remember that elements in the standard state will have an enthalpy of formation of 0, because you don't need to actually make them. So they have delta HF, which is equal to 0. So if I say delta HF of sodium, that's 0, because you can't. I mean, there's no energy needed to make sodium from its elements. Delta HF of O2, that's 0 as well. Okay, so keep that in mind. So that's enthalpy of formation. That's the first one. What's the next one they're talking about? They're talking about the next one they're talking about is what it is the ionization energies, which you already know. What's the definition of ionization?
Is it the amount of energy required to remove 1 mole of gaseous electrons from an atom?
Not the electrons being gaseous. It's from a gaseous atom. So the first
Oh.
ionization energy is that it's the energy that is always needed. It's always into. The first ionization energy is the needed amount, the energy that is needed when, or what happens when 1 mole of electrons are removed. So from 1 mole of gaseous atoms to form 1 mole of gaseous plus 1 ions. Positive 1 ions. The equation for this could be that you got sodium, it's gaseous, any element, you remove 1 mole of electrons from it. And if you do that, it's going to become Na plus 1 and gaseous plus 1 electron. So that's the first ionization energy. What could be the equation for the third ionization energy of aluminium? How would you write it?
Al2 plus gas goes to Al3 plus E minus.
Okay, so it's Al2 plus gas. It's turning into Al3 plus gas. Plus 1 electron. So that's your third. So what are the factors on which ionization energies, factors that affect ionization energies? Like what are the four main factors? What are the four main factors?
The distance between the nucleus and the electrons.
Equidistance or from nucleus, it's also, you can call it or refer it to as the atomic radius. or the ionic radius if you're removing it from an ion. What's the next one?
Is it the nuclear charge?
You get nuclear charge,
Shielding.
or the number of protons. You said shielding. And what's the fourth one?
The charge on the ion.
You get the net positive charge. And the fifth has something to do with orbitals. But we'll discuss the details later on. I mean, we actually don't need to discuss this in Born-Haber cycle, but just very quickly that down the group, the ionization energies decrease. Like when you move in the pure table, let's do that quickly. So down the group, what happens? It decreases. And why does it happen? Because atomic radius increases and shielding increases. So that's why, so despite the fact that protons, one of the factors against it, so despite the fact and then there's across the period, ionization energy increases across the period as well. Why does that happen? Because you got more protons. And you have
Sorry to cut you off, but are you recording this lesson or did I accidentally press a button?
I'm recording it.
Okay.
You get same shielding, and I'll share the folder where it's going to be kept. Okay. Just a second. So you got same shielding, and you've got what else? Increase across the period, and the other thing is that uh, distance also slightly decreases, very slightly decreases. So anyways, do you remember all of this down the group and across the period?
Yeah.
So then you have 1 second. So the next thing is so that's ionization energy. You're trying to remove electrons, right? So you've already done that. The next thing that we have to do is the enthalpy change of atomization. Uh, so standard, it's delta H. This is the standard. This is one that we did not do in AS. So standard enthalpy change of atomization, It's basically you're creating one mole of atoms. Like if I have an element, that element will be turned into 1 mole of gaseous atoms. Now to do this, you would have to break bonds. So hence it's always going to be endothermic. So you're going to take an element and you're going to break it into atoms. So when you're breaking bonds, that's going to be endothermic. Is that clear, Varda?
Yep.
So if I have a Cl2 molecule, I would have to break the Cl2 bonds and I'll get Cl atoms. But it has to be 1 mole of Cl atoms. So I'll be breaking half moles of Cl2 molecules. So in this case, this will be the enthalpy change of atomization of, so that's your enthalpy change of atomization of Cl, which is basically equivalent to, in this case, equivalent to, that's a gas. So that's equivalent to the bond energy or half the bond energy of a Cl-Cl bond. Right? Is this clear that in this case, you're just breaking Cl-Cl bonds, right? Okay.
Yep.
And similarly, you can have sodium. For sodium, it's going to be sodium that's solid, and you can break its bonds, metallic bonds in this case. So it will turn into sodium gaseous atoms. Well, you can't use bond energies over here because bond energies are only defined for gaseous molecules. So this is equivalent to enthalpy of atomization of sodium. You are breaking bonds, but you don't have bond energies for metallic bonds. So also remember, bond energies are only defined for gaseous molecules, covalent molecules. Okay, so is that clear?
Yep.
And so that's enthalpy of atomization of standard enthalpy change of atomization. The definition is that it's the energy that is always needed to do what, to break, to form 1 mole of gaseous atoms. From what? From elements in this standard state. So that's bond enthalpy, and so that's our bond energy. And the next thing we have is that it's about bond energies. Which atoms make stronger bonds? Do you have any idea which atoms make stronger bonds?
No.
Always remember, smaller atoms make stronger bonds because they're small, and therefore the shared electrons are very close to the bond length is smaller. So smaller atoms, plus they're less shielded as well, so they're more attracted to the shared electrons. So they are less shielded, have smaller bond lengths, Hence, they have stronger bonds. And larger enthalpy change of atomization. So is this part clear?
Yeah.
अच्छा अब ये है कि अच्छा what's the next one? The next one is, let me just add this. So the next one is, second. So the next one is bond enthalpy, which is bond energy. We have already studied that, but let's revise that quickly. So bond energy or bond enthalpy, it's basically the energy that's required to break a bond. And specifically break one monobonds of the same type. In what? So in gaseous molecules. So it's only defined for gaseous molecules, and the bonds have to be of the same type. So that's what your bond energy is. So for example, if I have this equation, CH4 gas turning into carbon gas and 4H gas. How many bonds did I break?
4 bonds.
So 4 bonds of CH have been broken. And bond energy is endothermic. It's positive because you're breaking bonds. So it's always endothermic, it's always positive. So we've broken 4CH bond. And also remember that in bond enthalpy, you've got exact values. So there are two types of bond enthalpies. Both are, you got exact values for molecules that have exactly the same type of bond. That have exactly, same type of bond. Or that have just one bond. That's.
What do you mean by exact values?
For example, if you look at a Cl2 molecule, it's there's exactly just one type of bond. That's it. So every time you break that, you're going to get exactly the same value, right? Is that clear? Well, is this clear? Can you hear me? Hello.
I can't hear you properly.
Can you hear me now?
Yeah, I can hear you now.
So I said
I
that.
didn't hear what you said.
So then I was saying that. Is this part clear that a chlorine molecule always has exactly the same type of bond, right? Because there's only one type of bond, right? Is that clear?
Yeah.
So it's going to have average values. It's going to use average values for a bond for larger complicated molecules. An example is that if I have an aldehyde, right? It's got how many CH bonds? It's got 6 CH bonds, right? I mean, it's got a CH bond over here, it's got a CH bond over here, and it's got a CH bond over here as well. Plus this other CH bonds, it's got a CH, this one's got a CH. And then there's one more CH bond, which is which is this one. But not all of them are exactly the same. Hence, average values are used. Is this clear? Whether is this clear?
I didn't hear you, and I can't see the screen either.
I'll just hold on a second.
I can see it now.
Okay, no, I was just saying that. Do you understand the average value part? Like, not all the CH bonds are exactly the same.
No, I didn't hear what you said.
I was just saying that, like some molecules, small molecules, they just have one type of bond, exactly one type. So in that case, you get the exact value for bond enthalpy. But for bigger, complicated molecules, if I talk about the CH bond, they're not all of the CH bonds, they're not exactly the same. Do you get this point? Like this CH bond is
Yes.
different compared to the CH3 CH bonds over here. So which is why, but since they are CH bonds, you take the average, but they're not all exactly the same, but you use the average values in this case. So sometimes for bond energies, you have to use average values, while in other times, you get exact values. I mean, that's the whole point. Okay. Now, so that's bond enthalpy. And we used to have a formula for calculating enthalpy change using bond enthalpies, and that was bonds broken is endothermic minus the bonds that are formed. So this was a formula, and but it can only be used for gaseous molecules. You have to be only use it for gaseous molecules. So next one. The next one is electron affinity. Where's the Yeah, lost the board just a second. As it's over here. I said the next one is electron affinity. Do you know what electron affinity is?
No.
So electron affinity is kind of the opposite of ionization energies. I mean, it's exactly the opposite of ionization energy. Basically, you're trying to add electrons. So it's the energy that is released or absorbed. It could be endo or exo. When what happens when 1 mole of gaseous atoms gain electrons? To form 1 mole of gaseous -1 ions. So that's what electron affinity is. So if I have a Cl atom, that Cl atom is going to gain 1 electron. It's going to become Cl -1 gaseous. Is this clear?
Yep.
And you don't really talk about like not like in ionization energies, you would actually talk about all the ionization energies, right? Like even the 10th and the 11th. Usually in electron affinity, you just talk about those electron affinities which apply to the element. For example, for Cl, you'll only be talking about the first electron affinity, not the second one, because Cl usually just gains 1 electron. For oxygen, you'll be talking about the first and the second. So what's the equation for the second electron affinity of oxygen? What would you call it? Like what? How would you write this equation?
Is it O minus gas plus E minus goes to O2 minus?
Okay, that's it's going to be O -2 gas, right? So that's what electron affinity is. Now the first electron affinity, remember, is always exo. So it's always exo, while the rest are all endo. As it becomes harder for negative ions to gain electrons due to repulsion. So the first electron affinity is always exo, while the rest are all endo. For example, for Cl, it's not difficult for it to gain electrons because Cl is a neutral atom. But for oxygen -1, because it's a negative ion, it's harder for it to actually gain electrons. Is this clear?
Yep.
So, and then in electron affinities, what happened here? Just a second. So also in electron affinities, what's going to happen is that uh, trend trends of electron affinities in group 17 or down the group, simply down the group. What do you think is going to happen? Like chlorine, who really likes to gain electrons out of all these four elements?
Is
Like
it iodine?
iodine, remember, is a big atom. It's very shielded. So would it like to gain more electrons, or would it be very hard for it to gain electrons?
Oh, it would be hard for it to.
Yeah, so it's, I mean, they're
So
more,
fluorine.
yes, it's, so down the group, they're more shielded, uh, bigger atomic radius. So more difficult to gain electrons. So less energy would be released. So they should become less exothermic. And here's just let me sum this up that electron. Just so do we have values for electron affinity? Just a second. Is this one. Now there's so it is decreasing. It is becoming exothermic. There's one exception, and that exception is fluorine. So you can see that fluorine has a slightly less exothermic compared to chlorine. And the reason for that is that fluorine is such a small atom that it's got very high charge density lone pairs, which repel electrons. So it kind of becomes harder for fluorine to actually gain electrons because it's so small and the electrons are already so crowded because they're very close to each other that fluorine's electron affinity is actually less exothermic compared to chlorine. Otherwise, the trend is followed except for fluorine. Is that clear?
Yeah.
So that's it. So that's all the definitions. Electron affinity is all about gaining electrons. That's it. While we had bond energy, which we had done earlier, enthalpy of atomization, TK, that's new. And we've got ionization energy, that's old. And you've got standard, that's also old, TK. We're gonna try and do next class. We'll do the bond Haber cycle, which is which is the next thing. Just a second, Western. So define each term. So basically, we just have to do the bond Haber cycle now. TK, we're done with the definitions. TK, clear?
Yeah, it also says something about lattice enthalpy as well.
Oh, why did they not give lattice enthalpy over here?
I think it says it in the first bullet point.
Hey, which one? Oh, we missed
It
this.
says define.
TK, that's the most
Yeah,
important.
yeah.
That's the most important one because that is what bond Haber cycle is used to calculate. So that's the main one basically. So we'll do that. That's what you're going to try and calculate using bond Haber cycle. So we're going to discuss lattice enthalpy tomorrow then. Okay.
Okay.
Take care.
Okay, thank you. I love this.